The topic is volume by cross-sections, which we sometimes call volume by slicing. You'll see why we use the term slicing in a minute. Um, in order to start understanding volume and how that fits into integrals, let's think about the most basic formula for volume that you all know, which is the formula for the volume of a rectangular solid or a rectangular prism. When we want to find the volume of a rectangular solid, what we do is we ask what are its dimensions in the three directions. You can label them sometimes width, depth, and length, width, length, and height, as I've done here. So let's say that this is the width of the rectangular solid, and the distance reaching back into the page, that's the length, and the distance up and down, we'll call that the height. So we all know that the volume of this solid is length times width times height. But there's actually another way to look at this. Let's suppose that instead I want to look at what the area of a cross-section is. So let me just draw in, pick a better color here. Let's draw in one cross-section. And when I say a cross-section, what I mean is if I actually took a knife and cut through this solid perpendicular to one of its directions. In this case, I'm taking a knife, I place it perpendicular to the width direction, and I take just a slice of this solid. And what I'd get, if I looked at the end of it, is I would get a rectangle. I would get a rectangle whose height is h and whose length is L. So if I wanted to find the volume of the solid using this rectangle, this purple rectangle, I could also write that the volume is equal to the area of one cross section times the width. In other words, this width, W. So this is kind of a useful way to think about how we would find the volume of a solid when we start to integrate, because what you're going to see is that the cross-sectional area of the solid becomes very important in forming the integral. Before I go on, I just want to emphasize that you already know a formula that looks like this. Let me just turn to the next page. Consider the volume of a cylinder. Many of you know that the volume of the cylinder is given by this formula, V equals pi r squared h. But if you think about what's really going into that, we're assuming that if I have a cylindrical can, such as the one shown on the right side of the screen, it has a circular base whose radius is r. So we know that the area of that base, is pi r squared, just the formula for the area of a circle. So if I look instead at, let's choose this color here, at one cross section, it's going to have the same area as the base, and what I'm doing is I'm taking the area of that cross section and multiplying it by the distance from one end of the solid to the other in a direction that is perpendicular to that cross section. So if we imagine this cross section being a circle, the side of the can is at right angles. Oops, let me do that. The side of the can is at right angles to that cross section. So the distance h, it proceeds in a direction perpendicular to that cross-sectional circle, and the area of and the volume of the full cylinder is just given by the area of the cross section times the full distance h from the bottom of the circle to the top. To go from finding volumes of rectangular solids or cylinders to finding volumes of more general objects, we want to be able to do is write the area of a cross section as a function of some variable. So consider the solid that you see in this drawing. Here, we clearly can't say that there's one cross section of the solid in the x direction. In other words, if I'm proceeding in the direction, get the yellow highlighter up here, if I'm proceeding in the x direction and I take a knife and slice this solid, I can't say that there's one cross-sectional area. As we can see, here's a very tiny area, here's a somewhat bigger area, here's an even bigger area. Where what the cross-section is, what the cross-sectional area is, depends on how far along the x-axis we are. But it turns out that that's perfectly fine, and I'll show you why. Because what I can do is, let's suppose that I have this cross. Let's pick let's pick x1. Oops. Let's pick x1. So if you look at the cross-sectional area right here, I can't just add up areas, because an area is just a flat object. But what I could do is I can extend this a tiny little bit in that direction. And guess what we're going to call that? We're going to call it dx. Why? Because that's what we always call an area. That's what we always call a tiny bit of distance in the x direction. So now, instead of having just a circle, which is just a flat object with no volume, what I have here instead is a circular disk with a tiny little bit of volume. So what's the volume of this disk? Volume of thin disk is going to be equal to the yellow area times dx. In other words, this is the cross-sectional area, and this is its length perpendicular to that, and perpendicular to the cross-section. The thing that's nice here is that I can determine what the cross-sectional area of this solid is as long as I know what the x position is. I'm going to get one cross-sectional area if I'm sitting right here over x1. I'm going to get a different cross-sectional area if I'm sitting over x2, and a third one if I'm sitting over x3. But I can write out the volume of a typical slice this way. Let's choose this color pen, of a typical slice. And I'm using the word typical in the same sense as the video you already watched on what's in an integral, the same way we had the area of a typical rectangle. Now I can talk about the volume of one typical slice somewhere along the length of this object. So the volume of a typical slice is going to be a of x dx, where this is the cross-sectional area and this is the length perpendicular to that cross-section. Well, guess what we can do in order to find the volume of the full object? We can simply add up all of those cross-sectional areas, all of those little slices, like this. Remember, the integral sign looks sort of like an S for sum, and we integrate from the lowest possible x value, which is a on the left, to the highest possible x value, which is b on the right. We're integrating from a on the left to b on the right. The way our textbook is going to describe this, actually, is it's going to point out that x equals a, now that we're looking in 3 dimensions, actually defines a slightly different color here. Which color do I want to use? I'll use that one. Actually defines kind of a plane on one side of the object, and then on the other side of the object we have this different plane. So this plane is x equals b, and this plane is x equals a. Now I know some of you are going to recognize that x equals a and x equals b are normally a line, but that's when we only have directions x and y. And as you can see, I have this space going backwards in what you can think of as sort of a z direction. So that's why you get a plane on either side. I don't want you to get too confused by the way the textbook describes this in terms of the language of a plane on either side of the object. The important point is that we know that this object that I've drawn extends from a low possible x value of a up to a high possible x value of b, and that's where we're getting the bounds on the integral. So this is the basic formula for volume by slicing, is we're going to integrate from a to b the area of a cross section over and in the direction perpendicular to that cross section. So integral from a to b of a of x dx is the basic formula that we use to find volume.